Imagine looking up at the night sky on a clear, star-filled evening. You see countless twinkling lights scattered across the darkness, each one a distant sun, each one part of something far greater than our own little corner of space. But what if I told you that even in our own cosmic backyard, within the unimaginably vast Virgo Supercluster that contains our Milky Way, there are secrets hiding in plain sight that defy everything we think we know about the universe? Mysteries so profound that they challenge the very foundations of physics and leave even the most brilliant scientists utterly baffled. These aren't just curiosities, they're cosmic puzzles that could reshape our understanding of reality itself. Welcome to a journey through space and wonder, where we'll explore 25 of the most astonishing unexplained phenomena right here in our local neighborhood of the cosmos. From galaxies that shouldn't exist to forces we can't measure, from strange signals to mysterious structures that hint at realities beyond our own, each one of these enigmas invites us to question, to imagine, and to dream bigger about what might be possible. This isn't just a list of oddities, it's an invitation to explore the very edges of human knowledge, to stand at the frontier of discovery and peer into the unknown. So get ready to venture beyond the familiar and into the extraordinary. Whether you're a seasoned space enthusiast or just curious about the universe's greatest secrets, this exploration promises to leave you awe-inspired, questioning, and maybe even seeing the night sky in a whole new light. Together, we'll unravel mysteries that have puzzled astronomers for decades and uncover the hidden wonders lurking in the Virgo Supercluster. The cosmos is calling, let's answer. Our journey into the cosmic unknown begins not in the far reaches of the supercluster, but much closer to home, with a mystery rooted in the very heart of our local galactic neighborhood, the Virgo Cluster itself. This dense collection of over 1,300 galaxies, the closest large cluster to our own, holds a secret in its motion, a puzzle astronomers call the Virgo Velocity Anomaly. For decades, scientists have meticulously mapped the movements of these galaxies by studying their light. As a galaxy moves away from us, its light is stretched, shifting toward the red end of the spectrum. This redshift allows us to calculate its velocity. By compiling these measurements from vast surveys, astronomers can create detailed velocity maps of the entire cluster, essentially creating a cosmic speed chart for hundreds of galaxies. What they found was utterly perplexing. According to our fundamental understanding of gravity, primarily governed by Einstein's theory of general relativity, the motion of these galaxies should be predictable. The immense gravitational pull of all the visible matter in the cluster, the stars, the gas, the dust, should dictate how quickly each galaxy orbits the cluster's center. The calculations are clear, but the observations are not. The galaxies are moving in ways that simply don't add up. Their velocities are far too high. They are whizzing around with a ferocious energy that the collective pull of all the visible stuff we can see cannot possibly contain. It's as if you saw a group of children on a merry-go-round spinning at an impossible speed. But when you looked for the motor, you found nothing, just the children themselves, incapable of generating that force. This discrepancy points to one of two monumental possibilities, each one revolutionary in its own right. The first and most widely accepted explanation is the existence of hidden mass, a vast amount of material that neither emits nor reflects light, completely invisible to our telescopes. This is what we call dark matter. Its gravitational influence would provide the extra pull needed to explain the galaxy's frenetic pace, acting as an unseen anchor holding the entire cluster together. The Virgo Velocity Anomaly becomes one of the strongest local pieces of evidence for this mysterious component that makes up the majority of matter in the universe. Yet, there is a more radical alternative. What if our understanding of gravity itself is incomplete? A minority of physicists propose that on the grand scales of galaxy clusters, gravity may not behave exactly as Einstein predicted. Theories of modified Newtonian dynamics, or MOND, suggest that the laws of gravity change slightly at these immense scales, creating stronger effects that mimic the presence of unseen matter. In this view, there is no dark matter. Instead, we are witnessing the subtle breakdown of our most fundamental cosmic rulebook. The anomalous velocities aren't caused by an invisible actor, but by a flaw in the script of physics itself. This single observation in the Virgo cluster forces us to confront the very limits of our knowledge, questioning whether we are missing a key ingredient in the cosmos or misreading the recipe entirely. But the gravitational strangeness within the Virgo supercluster doesn't end with invisible matter or rewritten laws. It points to an even more fundamental cosmic accounting error, one that involves the very stuff you and I are made of, normal matter. This brings us to our next profound mystery, the case of the missing baryons. In the grand ledger of the universe, cosmologists have a very precise inventory based on the afterglow of the Big Bang, the cosmic microwave background. This primordial light tells us exactly how much ordinary, or baryonic, matter, protons, neutrons, and electrons should have been created in the universe's fiery birth. This includes everything from stars and planets to vast clouds of gas and dust. When we apply this cosmic budget to our local universe, the Virgo supercluster should be brimming with a specific, predictable amount of this normal matter. Yet, when astronomers add up everything they can actually see and detect, all the stars in all the galaxies, all the glowing nebulae, all the planets and asteroids, the sum is shockingly inadequate. A staggering 30 to 40% of the normal matter that should be there is simply unaccounted for. It's as if you meticulously calculated the ingredients for a giant cake, but after baking it, you found that almost half of the flour had vanished into thin air. The cake exists, but a fundamental part of its composition is missing without a trace. So, where could it be hiding? Scientists have turned their most powerful tools toward solving this case. One prime suspect has been vast reservoirs of incredibly hot, but very diffuse, gas floating in the spaces between galaxies. This gas is so hot it doesn't emit visible light. Instead, it glows in high-energy X-rays. Powerful space telescopes like XMM Newton and Chandra have indeed stared deep into the heart of the Virgo cluster and found enormous halos of this million-degree plasma. These observations revealed some of the missing mass, but not nearly enough to balance the books. The amount of hot gas discovered, while immense, still only accounts for a fraction of the deficit. The hunt then expanded to the largest scale of all, the cosmic web. Our best models of the universe suggest that dark matter forms an invisible skeleton, and ordinary matter is drawn along this framework, creating a vast, interconnected network of filaments. Theorists propose that the missing baryons could be hiding in these tendrils as a form of warm-hot intergalactic medium, or WHIM. This matter would be even more tenuous and difficult to detect than the cluster gas. By using distant quasars as cosmic flashlights, astronomers have searched for the faint absorption signatures of this WHIM as its light passes through these invisible filaments. Again, they found some thin wisps of oxygen and other elements heated to temperatures of hundreds of thousands of degrees, and again, it wasn't enough. Each new observation recovers a little more of the missing matter, but the grand total always falls short of the theoretical prediction. This leaves us with a baffling paradox. We are confident in our inventory from the early universe, and we are confident in our methods of detection. Yet, the two refuse to reconcile. The missing baryon problem suggests that normal matter exists in a state or in a location we have not yet learned to observe. It could be locked in forms that are completely dark to our current technology, or it could be distributed in such a diffuse way across the supercluster that its signal is lost in the noise of the cosmos. This isn't about exotic dark matter. This is about the ordinary atoms that build everything we see and know, playing an elaborate game of cosmic hide and seek, reminding us that even the most familiar components of the universe can still hold profound secrets. Just as we grapple with the absence of normal matter, the presence of the universe's dominant ingredient, dark matter, brings its own set of profound puzzles. We've built entire cosmological models on the idea that this invisible substance forms a smooth, massive halo around every galaxy, providing the gravitational scaffolding for everything we see. But when we look closely at the galaxies within the Virgo cluster, this elegant picture begins to fray at the edges, revealing a distribution so strange and uneven it forces us to question our most basic assumptions. To even begin to map the invisible, astronomers rely on two powerful techniques. The first involves watching how stars move within a galaxy. According to Kepler's laws of motion, stars on the outer edges of a spiral galaxy should orbit more slowly than those near the center, much like the outer planets in our solar system have longer years. But when we measure these rotation curves, we find something astonishing. The stars on the galactic outskirts are moving just as fast as those near the core. The only way this makes sense is if a huge amount of unseen mass is enveloping the galaxy, its gravity pulling on those outer stars and whipping them around at impossible speeds. We can plot these velocities on a graph, creating a rotation curve that should fall but instead stays flat, a classic and powerful signature of dark matter's presence. The second method uses the universe itself as a magnifying glass. Einstein's theory tells us that massive objects warp the fabric of space-time, bending the path of light. When a massive galaxy cluster sits between us and a more distant object, its immense gravity can act as a gravitational lens, distorting the background light into spectacular arcs and rings. By meticulously mapping these distortions, we can create a detailed mass map of the foreground cluster. The result is a picture of where the gravity, and therefore the mass, is strongest. Time and again, these maps reveal massive gravitational anchors that correspond to nothing visible in our telescopes. They are the literal fingerprints of dark matter. For the most part, these methods confirm the dark matter model, but then we peer into the Virgo Supercluster and find glaring exceptions: galaxies that simply don't play by the rules. Take the fascinating case of Dragonfly 44, a galaxy so diffuse it's barely there. It has very few stars, yet its stars are moving at tremendous velocities. The rotation curve is incredibly flat, indicating a colossal amount of dark matter, so much that this ghostly galaxy is estimated to be 99.99% dark matter. It's a dark matter galaxy that just happens to have a few stars in it, a clump of invisibility that defies our understanding of how matter congregates. On the opposite end of the spectrum, we find galaxies that appear to have no dark matter at all. A prime example is NGC 4504, also in Virgo. When astronomers measured its rotation curve, they expected the familiar flat line. Instead, they found a curve that drops off perfectly, exactly as Kepler's laws predict for the visible matter alone. The stars move precisely as they should if only the stars, gas, and dust are pulling on them. It's as if this galaxy exists in a universe without dark matter, a stunning anomaly that should be impossible if dark matter is a universal component. How could one galaxy be made almost entirely of dark matter while its neighbor, formed in the same cluster environment, has somehow managed to rid itself of it completely? These extreme examples are more than just curiosities. They strike at the heart of our simulations, supercomputer models that simulate the evolution of the universe under the rules of the standard dark matter model, known as lambda cold dark matter, produce galaxies that look very much like our own. But they have an incredibly difficult time creating galaxies that are either overwhelmingly dark or completely devoid of it. The models predict a much more uniform and predictable distribution. The existence of these outliers suggests that our understanding of how dark matter interacts with itself or with normal matter through forces other than gravity might be critically incomplete. Perhaps dark matter can be stirred up and stripped away in violent galactic interactions within the dense cluster, or maybe there are different types of dark matter with varied properties. Each of these Virgo galaxies is a natural experiment, challenging us to refine our theories or perhaps even start from scratch. These ghostly giants are known as ultra-diffuse galaxies, and they represent one of the most visually striking paradoxes in the cosmos. Picture the Milky Way, our home galaxy, with its brilliant, star-packed spiral arms containing hundreds of billions of suns. Now, imagine an object of similar colossal size, stretching tens of thousands of light years across, but one that has almost none of those stars. If you were to fly through it, the space between each solitary star would be so vast, so profoundly empty, that you might not even realize you were inside a galaxy at all. It would be a cavern of near-total darkness, a ghost ship adrift on the cosmic sea. The discovery of these ultra-diffuse galaxies, particularly in the dense environment of the Virgo Cluster, was a moment of pure astonishment for astronomers. For so long, our telescopes simply weren't sensitive enough to see them. Their few stars were so spread out that their light blended into the background glow of the night sky. It was like trying to spot a single, dim light bulb from miles away on a foggy night. The development of new, incredibly powerful instruments like the Dragonfly telephoto array, which uses an array of commercially available camera lenses to minimize scattered light, finally peeled back the veil. What they revealed was a hidden population of these faint giants, with Dragonfly 44 becoming the most famous example. The immediate and pressing question was, what holds these wispy collections of stars together? According to all known physics, a galaxy so large yet so devoid of mass should be torn apart by the gravitational tides of its neighbors. The Virgo Cluster is a galactic metropolis, a crowded and violent place where galaxies constantly interact and even collide. A fragile object like an ultra-diffuse galaxy should be shredded to pieces in such an environment. The fact that they not only exist but are surprisingly common is a clear signal that something invisible must be providing an immense gravitational anchor. This is where the plot thickens dramatically. Measurements of the stars within Dragonfly 44 show they are moving at tremendous speeds. If the visible mass was all there was, those stars should have flown off into intergalactic space long ago. The only way to explain their rapid orbit is to infer the presence of a terrifying amount of dark matter. In the case of Dragonfly 44, calculations suggest it has a mass similar to the Milky Way, but 99.99% of that mass is completely invisible. We are looking at a dark matter halo that just happens to have a few stars sprinkled in it, a cosmic paradox that challenges our very classification of what a galaxy truly is. So how does something like this form? Astronomers are actively debating two compelling and opposing theories. The first posits that these are failed galaxies. In this scenario, a massive dark matter halo forms early in the universe, just like any other. Gas begins to fall into it, ready to cool and condense into a new generation of stars. But in the dense, hot environment of a cluster like Virgo, a process called ram pressure stripping might occur. As the proto-galaxy plows through the intracluster medium, the tenuous gas that is the raw fuel for star formation is violently ripped away. The galaxy is stillborn, left with its dark matter skeleton and the few stars it managed to form before its fuel supply was cut off. The second theory is even more intriguing. It suggests that these ultra-diffuse galaxies are actually the remnants of once normal galaxies that have been brutally ravaged over billions of years. As they orbit through the cluster, they could have countless close encounters with other galaxies. Each pass acts like a gravitational tide, pulling and stretching the galaxy, relentlessly plucking out its stars and gas. What remains is a dark matter core and a faint, diffuse shroud of the stars that manage to stay gravitationally bound. They are the survivors of cosmic violence, ghosts of galaxies past. The truth might lie somewhere in between, or could be a combination of both processes. What makes ultra-diffuse galaxies so crucial to science is that they are natural laboratories. They present extreme cases where the ratio of dark matter to visible matter is pushed to its absolute limit. By studying them, we can test the rules of how dark matter behaves. Does it interact with itself? Does it get stripped away during collisions, or does it just sink to the center? Each faint smudge of light in the Virgo cluster holds the answers, forcing us to refine our theories of not only galaxy evolution, but of the mysterious dark matter that shapes our universe. While we grapple with the ghostly presence of dark matter and the baffling absence of normal matter, our next mystery reveals a hidden force that weaves through the very fabric of the Virgo cluster itself. A force that is both invisible and incredibly powerful: magnetism. We often think of space as a true vacuum, an empty void where only gravity holds sway. But the space between the galaxies in Virgo is anything but empty. It is filled with a thin, hot soup of gas known as the intracluster medium. And permeating this entire vast expanse are magnetic fields of unexpected strength and complex structure, an invisible cosmic lattice that defies easy explanation. Detecting something you cannot see, especially across millions of light years, requires immense ingenuity. Astronomers turn to the field of radio astronomy to map these hidden forces. The key lies in a property of light called polarization. As electrons, accelerated by these magnetic fields, spiral along the field lines at nearly the speed of light, they emit a special kind of radio wave known as synchrotron radiation. This light doesn't just travel randomly, it becomes polarized, meaning its waves are oriented in a specific direction that is perpendicular to the magnetic field itself. By using enormous radio telescope arrays to carefully measure the polarization of this faint radio glow coming from the Virgo cluster, scientists can perform a kind of cosmic detective work. They can trace the orientation of the magnetic field lines back to their source, slowly painting a picture of this invisible scaffold that stretches across the entire cluster. What these observations reveal is astonishing. The magnetic fields are not weak or disorganized. They are surprisingly strong, coherent, and structured on a truly colossal scale. Imagine a magnetic field that is 1,000,000 times weaker than Earth's own protective magnetosphere. That might sound insignificant, but when that field is stretched across a volume of space millions of light years wide, its collective energy becomes staggering. These fields form vast, coherent patterns, with lines that appear to follow the subtle flows of the intracluster gas, often tracing the delicate filaments of matter that stretch between galaxies. They are a fundamental part of the cluster's ecosystem, influencing how the hot gas moves, how it cools, and how it might one day collapse to form new stars. Furthermore, these magnetic fields act as a guide and a trap for high-energy cosmic rays, the fastest particles in the universe, shaping their paths and preventing them from simply flying off into the void. The existence of these fields is clear, but their origin is one of the great open questions in modern astrophysics. How do you generate a magnetic field on a scale larger than a galaxy? The leading theory points to a process that sounds like science fiction but is grounded in well-established physics, the galactic dynamo. The basic idea is that any tiny, primordial seed of a magnetic field, perhaps one that has existed since the Big Bang itself, can be amplified and stretched by the motion of conducting fluids. In the case of a galaxy, that fluid is the plasma of the interstellar medium. As a galaxy rotates, its swirling motions can twist and shear these magnetic field lines, effectively turning the galaxy into a gigantic electrical generator that strengthens the magnetic field over billions of years. The theory suggests that when galaxies interact or merge within the cluster, they can spew out their magnetized plasma into the intergalactic space through powerful winds driven by supernova or active black holes. Over eons, this magnetized material from thousands of galaxies could be stirred and mixed by the gentle motions of the intracluster medium, eventually building up the pervasive fields we detect today. However, not everyone is convinced this dynamo process is sufficient. The fields in Virgo are so widespread and so well ordered that some scientists propose a more exotic primordial origin. Could these magnetic fields be a fundamental feature of the universe, woven into the cosmos at its very birth during a phase of rapid inflation? In this view, the fields weren't generated by galaxies but were imprinted on the fabric of space-time itself as the universe expanded from a subatomic point to cosmic size in a fraction of a second. These primordial fields would then have been there from the very beginning, providing the underlying structure that the cluster gas and galaxies simply fell into and now align with. This theory is far more radical, as it suggests magnetism is not an emergent property of galaxies but a fundamental force of the cosmos, as basic as gravity. The debate is far from settled, and each new, more detailed polarization map of the Virgo cluster provides another crucial piece of evidence in this cosmic whodunit, a mystery where the culprit could be the slow, collective action of galaxies or a relic from the first moments of time. Now, let's shift our focus from the silent, pervasive influence of magnetic fields to a phenomenon that announces its presence with a thunderous, if invisible, roar: the colossal radio halos and relics that engulf entire regions of the Virgo cluster. If we could see the universe with radio eyes, the serene optical view of this cosmic metropolis would be shattered. We would witness vast, ghostly clouds of emission, some spanning millions of light years, glowing with the energy of particles moving at nearly the speed of light. These are not galaxies, they are the aftermath of cosmic violence on an almost unimaginable scale, the fading echoes of the most energetic events in the universe since the Big Bang itself. To understand what we're seeing, we need to understand synchrotron radiation. This is the light emitted when electrons are accelerated to relativistic speeds and forced to spiral along magnetic field lines. The radio telescopes that map these structures, like the low-frequency array or the future square kilometer array, are essentially tuning into this specific signature. The resulting images are breathtaking. They reveal two distinct types of structures. Radio halos are immense, roughly spherical clouds that seem to sit at the very heart of a galaxy cluster, enveloping its core in a diffuse radio glow. Radio relics, on the other hand, are often found on the outskirts of clusters. They are more elongated and structured, frequently appearing as gigantic arcs or shock fronts, like the sonic boom from a supersonjet, but written across the cosmos in energetic particles. The prevailing theory for what creates these colossal structures points directly to the violent process of cluster formation. The Virgo Supercluster is not a static, serene place. It is a dynamic and evolving structure, and the Virgo cluster at its heart is still growing, accreting mass from its surroundings. When two smaller galaxy groups or subclusters collide and merge into a larger one, the energy released is beyond comprehension. These mergers are the most energetic events in the present-day universe. The chaotic turbulence and colossal shock waves that ripple through the intracluster medium during such a collision are perfect particle accelerators. They can take the sea of low-energy electrons and protons that already exists in the cluster gas and whip them up to phenomenal speeds, effectively turning the entire cluster into a natural particle accelerator far more powerful than anything we could ever build on Earth. This theory is elegant and compelling, but it faces some significant challenges when we look at the details. The first major puzzle is the sheer efficiency of the process. The turbulence and shocks from a merger are indeed powerful, but the physics of how they transfer their energy so effectively to electrons, and how those electrons then retain that energy for hundreds of millions of years to produce the extensive radio emission we see, is not fully understood. It's a bit like trying to figure out how a single lit match could set an entire forest ablaze in a rainstorm. The energy source is there, but the mechanism for spreading it so effectively is mystifying. Some physicists propose that we might be missing a part of the process, perhaps involving re-acceleration, where existing energetic electrons get a further boost from later, weaker shocks, keeping the radio glow alive long after the main merger event has concluded. An even more intriguing problem arises with so-called orphan or radio dark clusters. According to the merger model, only clusters that are currently undergoing or have recently experienced a major merger should possess these giant radio halos. Yet, when astronomers survey clusters, they find a confusing mismatch. Some clusters that are clearly undergoing a violent merger show no radio halo at all, while other clusters that appear relatively relaxed and quiet in optical and X-ray views nonetheless sport a giant, bright radio halo. This discrepancy suggests that our understanding of the triggering mechanism is incomplete. Perhaps the seeds for these halos are always present, and it takes a very specific type of merger or a particular state of the intracluster medium to ignite them. Or maybe there are other, unknown sources of energy capable of powering these immense structures. This leads to the most fascinating and speculative possibility that radio halos and relics might be the signature of something even more exotic. Could the particles be accelerated not just by gravitational shocks, but by the decay or annihilation of dark matter? If dark matter is made of theoretical particles like WIMP, their interactions could potentially release bursts of energy that feed these radio clouds. While this remains a highly speculative idea, it illustrates how these observations push us to consider physics beyond the standard model. The giant radio halos in Virgo are more than just pretty pictures. They are a direct window into the most energetic physics in the universe, a natural laboratory for studying particle acceleration and plasma physics on a scale we can never hope to replicate. They remind us that even in the vast, seemingly empty spaces between galaxies, there is a whirlwind of activity, a history of violence written in radio waves, waiting for us to decipher its full story. But the cosmic violence within the Virgo cluster isn't limited to the colossal, energy-drenched aftermath of galaxy mergers. Sometimes the most telling evidence of a struggle is found in the delicate, torn debris left behind by a single galaxy fighting for its life against an invisible foe. This brings us to the strange and beautiful case of galaxy NGC 4388 and its mysterious multi-tailed plumage, a celestial puzzle that requires the combined vision of our most powerful telescopes to even begin to unravel. Nestled within the heart of the Virgo cluster, NGC 4388 would be a fascinating object even without its bizarre appendages. It's classified as a Seyfert galaxy, which means it harbors an actively feeding supermassive black hole at its core, a monster engine that is voraciously consuming material and blasting out tremendous amounts of energy. This active galactic nucleus, or AN, makes the galaxy's center brilliantly luminous across the electromagnetic spectrum. But what truly sets this galaxy apart are the spectacular tails that stream away from it, stretching for thousands of light years into the blackness of the intracluster medium. Unlike a comet's single tail, NGC 4388 sports at least two distinct and massive tails, and they each tell a different part of the story depending on how you look at them. To understand this cosmic crime scene, astronomers had to become detectives, gathering evidence in different wavelengths of light. When they pointed radio telescopes at it, they observed a magnificent, long tail of emission stretching away from the galaxy's disk. This radio tail is believed to be synchrotron radiation, the telltale signature of high-energy electrons spiraling along magnetic field lines. It is a direct tracer of the galaxy's magnetic field being pulled out and stretched into space. Next, the Chandra X-ray Observatory revealed its own surprise, a large, diffuse cloud of extremely hot gas surrounding the galaxy and a separate, fainter X-ray tail. This is the signature of plasma heated to millions of degrees. Finally, optical telescopes like the Subaru telescope in Hawaii captured a more subtle tail of ionized hydrogen gas glowing a faint red. This is the stuff of stars themselves, the raw material of creation being forcibly ejected from its home. So, what powerful force is capable of simultaneously ripping a galaxy's magnetic field, its hot gas, and its star-forming material all out at once. The prime suspect in this celestial whodunit is a relentless process known as ram pressure stripping. The Virgo cluster is filled with that thin, but incredibly hot intracluster medium we discussed earlier. As a galaxy like NGC 4388 hurtles through this superheated plasma at speeds of thousands of kilometers per second, it experiences a phenomenal wind resistance, like sticking your hand out the window of a car moving at hypersonic speed. The force of this wind is so immense that it can overcome the galaxy's own gravity, which is the force that holds its gas and dust within its disk. The result is a cosmic stripping where the tenuous gas between the stars is violently swept away, leaving behind a trail of lost material that forms the tails we observe. In this scenario, the galaxy is a victim of its environment, having its lifeblood, the fuel for future stars, drained away as it orbits through the dense cluster core. However, there is another powerful player in this drama that cannot be ignored: the galaxy's own active supermassive black hole. The energy pouring out from the Aegean creates powerful jets and winds that blast outward from the galactic center. This internal activity could also be responsible for shaping and ejecting material, creating its own set of tails. Perhaps what we are seeing is not a simple case of external stripping, but a complex interplay between internal and external forces. The ram pressure might be compressing gas near the galaxy's center, funneling more material toward the hungry black hole and actually feeding the Aegean, making its outbursts more violent. Those outbursts could then blow material out into the path of the oncoming ram pressure, which then shapes it into the long tails we see. It's a feedback loop of cosmic proportions, where the cluster's environment aggravates the galaxy's internal monster, and the monster's rage in turn shapes how the environment affects it. The true answer likely lies in a hybrid of these two compelling theories. The multi-wavelength data is the key. The fact that the tails are observed in radio, optical, and X-ray light suggests that different components of the galaxy's interstellar medium are being affected simultaneously but in different ways. By meticulously mapping the location, shape, and physics of each tail, astronomers can work backwards to determine the primary force behind it. The long, continuous radio tail strongly points to the large-scale, directional force of ram pressure, which is excellent at dragging out magnetic fields. Meanwhile, the specific structures and energies within the X-ray and optical tails might hold clues to contributions from the Aegean's furious winds. NGC 4388 is not just a spectacle, it is a natural laboratory. By studying its torn and shredded forms, we gain a unique understanding of the physical conditions within the Virgo cluster itself, the density and pressure of the intracluster medium, and we learn how galaxies evolve, lose their gas, and ultimately die as they interact with their environment. It is a single, stunning snapshot of a galaxy in transition, caught in the act of having its identity rewritten by the powerful forces of its surroundings. But our exploration of the Virgo cluster's hidden structures doesn't end with the violent stripping of individual galaxies. If we look even deeper, beyond the brilliant cities of light that are the galaxies themselves, we find a far more subtle and pervasive glow, a faint cosmic twilight that fills the spaces between them. This is the intracluster light, a soft radiance from countless stars adrift in the abyss, and its unexpected brightness presents us with a profound paradox that challenges our stories of how clusters evolve. To witness this ghostly glow for yourself, you would need the capabilities of the world's most powerful telescopes and advanced image processing. Astronomers take long-exposure images with instruments like the Hubble Space Telescope or giant ground-based observatories. Then, through meticulous data reduction, they digitally subtract the overwhelming light from every single star and galaxy in the frame. What remains is not pure blackness, but an incredibly faint, uneven background of light. In enhanced false-color images, this intracluster light appears as a delicate web of bluish tendrils and a diffuse, golden haze, a cosmic fog connecting the brilliant islands of galaxies. It is the equivalent of seeing the scattered embers from a distant forest fire long after the flames have died down. For a long time, astronomers assumed this light was merely a minor byproduct of cluster formation, the scattered debris from cosmic car crashes. The prevailing theory was straightforward. As galaxies interact and merge within the dense cluster environment, the immense gravitational tides they generate pull and stretch them, ripping out streams of stars that can no longer find a gravitational home. These stars, once part of a galactic disk, are flung into the intergalactic void, destined to wander forever between the galaxies, their collective light forming this faint glow. It's a beautiful and tragic story, a narrative of cosmic violence leaving orphans in its wake. However, when scientists quantified this light, a major problem emerged. They ran sophisticated computer simulations of the Virgo Cluster's formation, modeling billions of years of galactic interactions and mergers. These simulations naturally produced intracluster light from this tidal stripping process. But when they compared their virtual results to the actual observations, the numbers didn't match. The real intracluster light in Virgo is significantly brighter, by a factor of 2 to 10, than what the simulations predict. The models, which are otherwise excellent at reproducing the cluster's large-scale structure, consistently underestimate the number of stars floating freely in intergalactic space. It's as if we calculated how much sawdust a woodshop should produce, only to walk in and find the floor covered in a mountain of the stuff. This discrepancy, the Virgo intracluster light paradox, forces astronomers to reconsider the origins of these lonely stars. The straightforward tidal stripping model is clearly not the whole story. So what other processes could be flooding the cluster with so much stellar light? One compelling idea is that the intracluster light isn't just from recent dramatic collisions, but is instead a cumulative record of the cluster's entire violent history. Every close encounter, every near miss, and every merger over billions of years has contributed a few more stars to the intergalactic population. Our simulations might not be capturing the full intensity and frequency of these smaller yet constant interactions. An even more intriguing possibility is that a significant portion of these stars weren't ripped out of mature galaxies at all, but were born in the wild. We know the intracluster space is not a perfect vacuum. It contains vast reservoirs of hot gas. Could dense pockets of this gas have collapsed under their own gravity to form stars completely independently of any galaxy? These would be true intergalactic stars born in the darkness between the galaxies. While it's a fascinating thought, the conditions required are extreme, and most astronomers find it a less likely contributor than other mechanisms. Perhaps the most radical solution is that we are underestimating the sheer number of tiny, faint galaxies that have already been completely dismantled. The Virgo Cluster is a gravitational slaughterhouse where small dwarf galaxies are especially vulnerable. Our telescopes might not be sensitive enough to see the final, most diffuse stages of a galaxy being torn apart. What we see as a smooth background glow could in fact be the unresolved light from the skeletal remains of thousands of these small galaxies that were entirely dissolved by the cluster's gravity. The intracluster light, therefore, wouldn't just be stray stars. It would be a galactic graveyard, the final glow of entire systems that have been erased from the cosmic map. This faint, elusive light is more than just a pretty picture. It is a direct fossil record of the cluster's assembly. By studying its brightness, color, and distribution, we are essentially reading a history book written in starlight, a narrative that tells us the Virgo Cluster's past was even more violent and chaotic than we ever imagined. Now, as we pull our gaze back from the individual tales of galactic disruption and look at the Virgo Cluster as a whole, we encounter a pattern so widespread and so counterintuitive that it points to a fundamental misunderstanding of how galaxies live and die. This is the mystery of the strangulated spirals, galaxies that appear to have all the ingredients for a vibrant future, yet have simply given up on creating new stars. It's as if you walked into a bakery stocked full of flour, yeast, and water, only to find the ovens cold and the bakers idle, with no clear reason for the halt in production. For a galaxy, the primary ingredient for star formation is cold, dense gas. This molecular hydrogen is the cosmic nursery, collapsing under its own gravity to ignite new suns. For decades, astronomers have used radio telescopes to map this gas reservoir in galaxies across the Virgo Cluster. The results are clear. Many spiral galaxies there are still incredibly gas-rich. They possess vast clouds of this star-forming fuel, sometimes holding billions of solar masses of the stuff. Logically, these galaxies should be bustling stellar factories, their spiral arms aglow with the blue light of massive young stars. But when astronomers cross-reference these gas maps with observations that measure actual star formation, like ultraviolet light from hot young stars or the specific infrared signature of heated dust in stellar nurseries, they find a shocking disconnect. The charts tell a story of sudden and unexplained silence. For a significant number of these gas-rich galaxies, the star formation rate has plummeted to near zero. The fuel is in the tank, but the engine has seized. This isn't a gentle slowing down. It's a cosmic traffic jam where the road is clear, but the cars have inexplicably stopped moving. So what cosmic mechanism could be preventing this plentiful gas from collapsing into stars? The investigation points to several prime suspects, each with a plausible motive, but none leaving a perfect fingerprint at the scene. The first suspect is the one we've already met, ram pressure stripping. As a galaxy plows through the intracluster medium, the intense wind could, in theory, be compressing the gas clouds in the galaxy's disk. While this might sound like it should trigger star formation, the opposite can be true. The process can heat the gas or strip away the outer, cooler layers of the molecular clouds, preventing them from reaching the critical density needed to collapse. It's like trying to light a firewood log with a blowtorch. The intense heat might char the outside, but it never allows a stable, sustained flame to catch hold within. The second suspect is the galaxy's own central supermassive black hole. In its active phase, an AGN can flood its host galaxy with powerful jets and winds. This immense energy input can heat the surrounding gas reservoir, effectively putting it on a permanent simmer that prevents it from cooling down and condensing into stars. This process, known as AGN feedback, is a key feature in many models of galaxy evolution, a self-regulating mechanism to prevent galaxies from growing too large. But the timing and intensity required to so completely and abruptly quench star formation, while leaving the gas reservoir largely intact, is difficult to reconcile with the observations. Then there are more subtle environmental factors. The constant gravitational jostling within a dense cluster can tidally shock a galaxy, stirring up its gas and preventing the quiet, calm conditions needed for star birth. It's the difference between trying to fill a glass of water from a tranquil stream versus from a raging, turbulent river. Yet for all these compelling theories, a puzzling discrepancy remains. When astronomers run sophisticated simulations that include all of these effects, ram pressure, AGN feedback, and tidal shocking, they still cannot fully reproduce the observed pattern. The simulations show a more gradual decline in star formation as gas is depleted or removed. They don't naturally create this large population of galaxies that are simultaneously gas-rich and yet completely quiescent. There appears to be a missing piece of physics, a hidden process that actively and efficiently suppresses star formation without destroying or expelling the gas itself. This leads scientists to consider more exotic possibilities. Could there be an unknown form of energy transfer within the intracluster medium that is preferentially heating the gas in these galaxies? Or perhaps the magnetic fields that weaves through the cluster play a more direct role than we thought, providing a supporting pressure that prevents gas clouds from collapsing under their own weight. The answer to this cosmic whodunit remains elusive. Each gas-rich, silent galaxy in Virgo is a silent witness to a process we do not yet understand, a process that may hold the key to predicting the ultimate fate of galaxies, not just in clusters, but throughout the entire universe. But our journey through the Virgo Supercluster's mysteries takes an even more dramatic turn as we focus our attention on a single, brilliant beacon at the cluster's heart, the colossal galaxy Messier 87. This giant elliptical galaxy is famous for the spectacular jet of plasma that screams from its core, a cosmic searchlight visible even in amateur telescopes. And at the very center of that maelstrom lies a gravitational monster so profound that we have actually taken its picture, the now iconic black hole image revealed by the Event Horizon telescope. Yet for all its fame, this supermassive black hole presents us with a profound and heavy mystery. It is simply too big for its cosmic home. To appreciate the scale of this enigma, we first need to understand the established rulebook. For years, astronomers have observed a remarkably tight correlation between the mass of a galaxy's central bulge, the dense spherical cluster of stars at its core, and the mass of its supermassive black hole. In most galaxies, the black hole's mass is almost exactly 0.1% of the bulge's mass. It's a consistent rule that suggests the growth of the black hole and the growth of its host galaxy are deeply intertwined, perhaps regulating each other through violent feedback cycles where the black hole's energy outflow stifles star formation. This relationship is a cornerstone of our understanding of galactic evolution. Then there is M87's black hole, weighing in at a staggering 6.5 billion times the mass of our Sun. This Leviathan doesn't just break the rules, it shatters them. Its host galaxy, while enormous, does not have a stellar bulge 10 times more massive still, as the correlation would predict. This black hole is overmassive, a gravitational sovereign that seems to have grown to a size that its galactic kingdom can no longer support. It's the equivalent of finding a tiny village that somehow contains a skyscraper larger than any building in New York City. The structure simply doesn't match its surroundings. So how did this black hole become so disproportionately huge? Astronomers are investigating two compelling and potentially intertwined explanations. The first points to the unique cutthroat environment of the Virgo cluster itself. M87 sits at the very gravitational center of the cluster, making it the ultimate cosmic trophy. Over billions of years, it has likely cannibalized countless smaller galaxies that strayed too close. With each merger, it consumed not just their stars but also their own central black holes. These smaller black holes would have sunk to the center of M87 through a process called dynamical friction, eventually merging with the central monster and feeding it a series of colossal meals. This hierarchical growth could have allowed it to pack on mass far more efficiently than a black hole in an isolated galaxy, which might only feed on the gas from its own disk. The second theory focuses on its unique accretion history. Perhaps M87's black hole had access to an unusually rich and long-lasting source of fuel. Instead of the typical feast or famine diet of most black holes, it might have enjoyed a continuous buffet. This could have been provided by a steady stream of gas funneled down from the vast reservoir of hot intracluster medium, or from the disrupted gas of the many galaxies it has consumed. If it fed in a special, stable mode for an exceptionally long time, it could have grown to its immense size without triggering the powerful feedback that normally shuts down growth and star formation in the host galaxy. In this scenario, it didn't just eat more, it ate smarter and for longer. The most spectacular evidence of this black hole's activity is its relativistic jet, a beam of magnetized plasma that stretches for thousands of light years. Simulations of this jet show how intense magnetic fields near the event horizon are able to capture some of the infalling matter and catapult it outward at nearly the speed of light. This jet is a direct manifestation of the monstrous energy generated by accretion, and its sheer power and stability hint at the incredible mass and spin of the black hole engine driving it. The existence of this overmassive black hole forces a critical re-evaluation of the black hole galaxy coevolution narrative. It suggests that in the densest environments in the universe, the rules are different. The standard feedback cycle may be overwhelmed or bypassed entirely by the extreme physics of cluster dynamics. M87's black hole stands as a monumental exception that challenges the rule, proving that while nature often follows patterns, it also reserves the right to create breathtaking outliers that force us to rethink everything we thought we knew. Moving beyond the silent struggles of galaxies and the ponderous weight of central black holes, our investigation turns to objects that are far more ethereal, yet just as puzzling. Vast clouds of hydrogen gas hurtling through the Virgo cluster at speeds that defy easy explanation. These are not galaxies, they are cosmic ghosts, immense structures of primordial fuel racing through space, and their very existence challenges our models of how clusters form and evolve. For decades, radio astronomers have been mapping the sky not in visible light, but in the specific radio wavelength emitted by neutral hydrogen atoms. Using colossal instruments like the now collapsed Arecibo Observatory and the Green Bank Telescope, they have conducted vast surveys, patiently scanning the Virgo cluster to create a three-dimensional map of its gas content. What these surveys revealed was a population of high-velocity clouds, enormous, isolated reservoirs of hydrogen gas, some containing enough mass to form entire dwarf galaxies that are moving on trajectories completely independent of the galaxies around them. Their velocities, sometimes hundreds of kilometers per second different from the systemic motion of the cluster, mark them as interlopers, rogue elements in the galactic ecosystem. The immediate mystery is their origin. Where did these massive, fast-moving clouds come from, and how have they remained coherent as they streak through the cluster's tumultuous environment? Several theories have been proposed, each with its own compelling evidence and confounding weaknesses. The first and most straightforward idea is that they are tidal debris, the gaseous equivalent of the stellar intracluster light. In this scenario, the violent gravitational interactions between galaxies have ripped giant streams of gas from their disks. Over time, the densest clumps within these streams could have condensed into the distinct clouds we observe today. This would neatly connect them to the same dynamical history that created the other forms of intracluster material. However, a closer look at their kinematics, their precise motions and locations, often fails to support this tidy story. For many of these clouds, astronomers cannot trace a clear path back to a parent galaxy. There is no obvious tidal tail connecting them to a recent collision, and their chemical composition sometimes differs from the enriched gas typically found within evolved galactic disks. This has led to a more exotic possibility that some of these clouds are not debris at all, but primordial relics. They could be leftover building blocks of the universe, pockets of pristine hydrogen and helium that never managed to collapse and form stars during the early epochs of cluster assembly. These ancient fossils would have been drifting through intergalactic space for billions of years, only now being detected as they pass through the modern cluster. A third, and perhaps most fascinating, hypothesis involves a process called ram pressure stripping itself, but with a twist. As a gas-rich galaxy falls into the cluster for the first time, the intense pressure of the intracluster medium can act like a cosmic squeegee, scraping the gas from the galaxy's disk. In some cases, this stripped gas might not immediately dissipate. Instead, it could be compressed into a large, coherent cloud that continues to coast along with the galaxy's original momentum, eventually becoming an independent entity racing ahead of or trailing behind its former home. This would create clouds that are not tidal in origin, but are rather the direct result of environmental pressure, a kind of galactic afterbirth left drifting in space. The true puzzle is that no single model can explain all the observed clouds. Some fit the tidal debris picture perfectly, while others align with the primordial remnant or ram pressure scenarios. This suggests that the high-velocity cloud population is not a single class of object, but a diverse zoo of structures with multiple origins. They are a cumulative record of every violent process that has ever occurred within the cluster, from ancient mergers to recent galactic infill. Each cloud is a unique fossil, and by studying its mass, velocity, and composition, we can piece together a specific chapter in the Virgo cluster's long and dramatic history. Their seemingly chaotic motions are not random. They are a complex dance dictated by the cluster's gravitational field and its history of cosmic violence, a dance we are only just beginning to learn how to interpret. But just as we begin to map the complex gravitational dance within the Virgo cluster, a far grander and more perplexing motion emerges when we pull our view back to the scale of the entire supercluster. Galaxies are not just moving in random orbits, they appear to be part of a vast, coherent river, flowing with a surprising and unexplained sense of purpose. This discovery, known as the dark flow, suggests that the gravitational influences shaping our cosmic neighborhood might extend from realms far beyond the edge of everything we can see. To grasp the sheer oddity of this phenomenon, we first need to understand the standard model of cosmic motion. The universe is expanding, a fact we've known since Edwin Hubble's seminal work. This expansion is often visualized as raisins in a rising loaf of bread, all moving away from each other as the dough itself expands. On top of this smooth, predictable expansion, we expect to see smaller, localized motions. These are caused by the gravitational tug of war between nearby structures. For instance, our Milky Way is gently pulled toward the massive Virgo cluster at the heart of our supercluster. These local flows are well understood and mapped with incredible precision. Scientists create these maps by first calculating a galaxy's expected velocity based solely on the universal expansion, a value known as its Hubble flow velocity. They then use instruments like the cosmic microwave background, the afterglow of the Big Bang, as a fixed reference frame to measure any deviation from this expected velocity. This deviation, called the peculiar velocity, reveals the direction and speed of a galaxy's true motion through space, allowing astronomers to chart immense cosmic currents. The shock came when astronomers, using data from a spacecraft called the Wilkinson Microwave Anisotropy Probe, began plotting these peculiar velocities for thousands of galaxy clusters. They discovered that these clusters were not just drifting randomly. Instead, a significant number of them, including our own Virgo Supercluster, were all streaming in the same general direction at speeds of nearly 1,000 kilometers per second. This wasn't a local flow toward a nearby attractor. It was a bulk motion on a scale of billions of light years, a coordinated drift that seemed to point toward a specific patch of sky between the constellations of Centaurus and Vela. The most baffling part was that the source of this immense gravitational pull appeared to lie far beyond the visible horizon of our observable universe. It was a flow towards something we cannot possibly see, a destination that remains forever out of reach. This observation immediately sparked intense debate and controversy within the cosmology community. The prevailing model of the universe, lambda cold dark matter, does not predict such a massive, coherent flow on such an immense scale. The gravitational influence of all the known matter in the observable universe should not be capable of generating this kind of bulk motion. So, if the observations were correct, it implied one of two revolutionary possibilities, each more mind-bending than the last. The first and most speculative theory is that the dark flow is evidence of a gravitational pull from a region of space-time outside our own observable bubble. In the theory of eternal inflation, our Big Bang may not have been a unique event, but merely one bubble in a vast, frothing multiverse of other universes. If another inflationary bubble existed relatively close to ours in the greater multiverse, its immense mass, even though it is in a separate space-time, could, in theory, exert a gravitational influence on our own universe, tugging our entire local cosmos in its direction. A slightly less radical but still profound explanation points to a colossal, unseen structure within our own universe, but one so vast it extends beyond our cosmological horizon. Just as the Shapley supercluster pulls us from one direction, there could be an immeasurably larger concentration of mass, a super-duper cluster of almost unimaginable proportions lying just over the edge of what we can observe. Its gravity would be felt by galaxies near the limit of our vision, creating the coordinated flow we detect, while the structure itself remains forever hidden by the curvature of spacetime and the finite speed of light. However, many scientists remain deeply skeptical. The primary counter-argument is that the dark flow could be a systematic error in the data analysis. The method of using the cosmic microwave background as a fixed reference frame is incredibly delicate. Subtle errors in calibrating the spacecraft's instruments or in modeling the complex physics of how hot gas in galaxy clusters interacts with the CMB light could potentially create a false signal that mimics a bulk flow. Subsequent studies using different methodologies and data from other telescopes, like the Planck satellite, have failed to confirm the original detection with the same strength, or have attributed the motion to known, albeit immense, structures within the observable universe. The controversy continues, with each new analysis and galaxy survey refining the measurements. Whether a confirmed reality or a tantalizing artifact, the concept of the dark flow forces us to confront the ultimate limits of our knowledge. It asks a humbling question: are the motions of our local universe dictated entirely by what we see, or could we be responding to the ghostly pull of worlds beyond our own? As we chart the grand currents of dark flow and the chaotic ballet of high-velocity clouds, our search for the supercluster's secrets brings us to a different part of the electromagnetic spectrum, where the universe reveals itself not in visible starlight or radio waves, but in high-energy X-rays. It is here, in the realm of the violently hot and the extremely dense, that some of the most perplexing signals have been detected: brief, brilliant flashes that appear without warning and then vanish, leaving behind a trail of questions and no clear answers. These are not the steady glows of supermassive black holes or the predictable pulses of neutron stars. They are cosmic transients, and their mysterious nature challenges our very catalogue of celestial objects. NASA Chandra X-ray Observatory, an unparalleled eye in the X-ray sky, has been instrumental in this detective work. By staring for long periods at regions within the Virgo Cluster, Chandra builds up incredibly detailed images where each pixel represents not a star, but a source of high-energy radiation. Most of these sources can be identified: the brilliant, active nuclei of galaxies, the hot intracluster gas, or binary systems where a star is being cannibalized by a compact object like a white dwarf, neutron star, or stellar mass black hole. The light curves of these known objects, graphs of their brightness over time, follow predictable patterns, flaring and fading in ways we understand, but then there are the outliers. The archives from Chandra and other X-ray telescopes like XMM Newton contain records of sources that defy this classification. They appear suddenly in a patch of sky that was previously dark at these energies. Their light curves show a rapid, dramatic increase in brightness, a spike that can last for hours or days before an equally rapid decline into nothingness. They do not repeat. They do not correspond to any object visible in optical, infrared, or radio telescopes. They are brilliant, one-off events that flare like cosmic flashbulbs in the depths of space and then are gone forever, their location offering no clue as to their origin. So what could possibly generate such a tremendous amount of energy so quickly and then disappear without a trace? Astronomers are actively investigating several compelling and quite exotic possibilities. The first candidate is a class of object we have long theorized about but have never conclusively found: intermediate mass black holes. We are familiar with stellar mass black holes formed from collapsing stars and the supermassive giants that lurk in galactic centers. But what about black holes in between, with masses of thousands or even hundreds of thousands of suns? Such an object could originate in the early universe or form in the dense core of a globular cluster. If a star wandered too close to one of these hidden monsters, the tidal forces would rip it apart in a spectacular event known as a tidal disruption event. This would create a sudden, short-lived flare of X-rays as the stellar debris is violently heated before falling in. A single, non-repeating flash in Virgo could be the signature of just such a rare, catastrophic snack. An even more speculative idea connects these events to the universe's most elusive substance, dark matter. Some theories suggest that dark matter could be made of particles that are their own antiparticles. If two of these particles collided, they would annihilate each other in a burst of energy, potentially producing gamma rays and X-rays. While we might expect this to produce a steady glow from regions dense with dark matter, it's possible that rare, concentrated clumps of dark matter could collapse or interact in a way that causes a sudden, explosive chain reaction of annihilations, a dark matter bomb flashing into existence for a brief moment. The clean, empty location of some of these X-ray flashes makes this tantalizing, if highly speculative, idea a topic of serious discussion. Lastly, we must consider the possibility that we are witnessing an entirely new type of astrophysical event. The history of astronomy is filled with discoveries that began as inexplicable anomalies. Pulsars, quasars, and gamma-ray bursts were all once baffling one-offs before they were understood and classified. These strange X-ray sources in Virgo could be the first hints of a new physical process, perhaps related to the extreme magnetic fields in the intracluster medium or a previously unknown phase in the evolution of binary stars. Each unexplained flash is a signal from the unknown, a message in a language we have not yet learned to decipher, reminding us that our inventory of cosmic phenomena is still far from complete. While we search for the source of unseen gravitational currents and fleeting X-ray flashes, our investigation turns to a more fundamental tension between prediction and observation, a puzzle that strikes at the very heart of how we believe structures form in the universe. This is the missing satellite galaxy problem, and it presents a stark contradiction. Our most sophisticated computer simulations of the cosmos create a universe that looks almost nothing like the one we actually see when we peer into the depths of the Virgo Supercluster. To understand this cosmic shortfall, we need to step into a virtual universe. Cosmologists run immensely powerful simulations, such as the famous Millennium Simulation or the more recent Illustris TNG project. These are not simple animations, they are complex mathematical models that code the entire known history of the universe into a supercomputer. They start with the conditions just after the Big Bang, a nearly uniform soup of matter and dark matter, and then let the laws of physics play out over billions of virtual years. Gravity acts on the dark matter, causing it to clump together into a vast cosmic web of filaments and halos. Ordinary matter, drawn by this gravitational scaffolding, then flows into these halos and condenses to form galaxies. The result is a breathtakingly detailed digital cosmos, a complete history of formation from the first moments to the present day. When scientists analyze these virtual universes, they find a very specific prediction about galaxy formation. Every large galaxy, like our own Milky Way or the great galaxies in Virgo, should be surrounded by a veritable swarm of smaller satellite galaxies. These satellites are the smaller dark matter halos that were captured by the larger galaxy's gravity but never fully merged. The simulations predict that a galaxy the size of the Milky Way should have hundreds, if not thousands, of these smaller companions orbiting it. They are the cosmic equivalent of moons around a planet, a bustling entourage of smaller systems. Armed with this prediction, astronomers turn their most powerful telescopes toward the galaxies in the Virgo cluster to conduct a cosmic census. They used wide-field survey instruments like the Sloan Digital Sky Survey to meticulously scan the skies, counting every single patch of light, every fuzzy dwarf galaxy that could be identified as a satellite around a larger host. The results were startlingly clear, and they completely defied the simulations. Instead of hundreds of satellites, they found only a few dozen. The predicted bustling metropolis of small galaxies was in reality a sparsely populated countryside. The universe, it seemed, had failed to build the vast majority of its predicted small-scale structures. This glaring mismatch between the virtual and the real is the core of the missing satellite problem. So where did all the satellites go? Astronomers have pursued two main lines of investigation to solve this case. The first focuses on the nature of dark matter itself. The standard simulations use a model called cold dark matter, which assumes dark matter particles move slowly and interact with each other and normal matter only through gravity. But what if that's not entirely true? Some theorists propose a tweak known as warm dark matter. In this model, the particles would be lighter and faster moving in the early universe. This extra motion would have a smoothing effect, wiping out the very smallest density fluctuations before they could collapse into halos. The result would be a universe with far fewer tiny dark matter clumps, and therefore far fewer tiny satellite galaxies. This would neatly solve the problem, but it comes with a trade-off, as warm dark matter might also struggle to form the very first galaxies quickly enough to match other observations. The second possibility is that the satellites were formed, but something prevented them from becoming visible. This is where the fascinating concept of observational biases comes in. The smallest, faintest dwarf galaxies are incredibly difficult to detect. Their stars are few and far between, and their light is so diffuse it easily blends into the background glow of the night sky. It's entirely possible that a large population of these ultra-faint dwarfs is hiding in plain sight, just below the detection threshold of our current surveys. Recent discoveries, like those from the Dark Energy Survey, have indeed begun to find a new population of these incredibly faint satellites around our own Milky Way, suggesting we are only just beginning to see the tip of the iceberg. However, even with these new additions, the numbers still fall short of the simulation's prolific predictions. There is a more brutal and definitive solution. Perhaps many of the satellites were destroyed. The Virgo Cluster is a dangerous environment, and the relentless gravitational tides from a large host galaxy could potentially rip apart a small satellite over billions of years, dissolving its stars into the diffuse halo of intracluster light we discussed earlier. The satellites may have been born, but they could not survive the violent dynamics of cluster life. Each of these explanations, from tweaking dark matter to finding faint dwarfs to invoking destruction, has its own merits and flaws. The missing satellite problem remains a vibrant and open area of research, a powerful reminder that even our best virtual universes are still only models. They are approximations of reality, and when reality pushes back, it forces us to refine our understanding of the invisible forces that sculpt the cosmos. Yet, even as we grapple with the absence of predicted satellites, our investigation into the Virgo Cluster's hidden mass takes a more direct and visual form, one that literally bends the fabric of reality to show us what our eyes cannot see. This phenomenon is gravitational lensing, the universe's ultimate tool for revealing the invisible, and within Virgo, it is producing bizarre effects that refuse to fit our models, pointing toward either elusive substructure or a fundamental rewrite of the laws of gravity. To understand this cosmic magic trick, we must first picture the universe not as empty space, but as a flexible fabric, a four-dimensional tapestry of spacetime. Einstein's theory of general relativity tells us that mass warps this fabric. The more massive an object, the deeper the dimple it creates. Now, imagine light from a distant galaxy traveling across the cosmos in a straight line. If its path takes it near a massive cluster like Virgo, the light will follow the curvature of this warped spacetime, bending around the mass like a marble rolling around the rim of a bowl. This bending of light is gravitational lensing. In its most spectacular form, strong lensing, the effect creates multiple images of the same background galaxy, or stretches it into brilliant, shimmering arcs and rings of light that encircle the foreground cluster. These are not photographic artifacts, they are genuine cosmic mirages, nature's own funhouse mirrors showing us the same object from multiple different paths through curved space. Astronomers use these exquisite distortions with the precision of master cartographers. By meticulously measuring the exact shape, position, and brightness of these lensed arcs, they can work backwards to create a detailed mass map of the foreground cluster. It's a process called lens modeling. They input all the visible matter they can see, the stars, the glowing gas, and then add the presumed distribution of dark matter in a smooth, diffuse halo, as predicted by the lambda cold dark matter model. The computer then calculates what the lensed images should look like based on that total mass. In many cases, the model and the observation match beautifully, providing some of the strongest evidence for the existence of dark matter. But in the Virgo cluster, there are glaring exceptions, cases where the real, observed arcs are kinked, twisted, or positioned in ways the smooth model simply cannot reproduce. The light is bending around something that isn't in the map. It's as if you were trying to predict the path of a river by mapping the visible hills and valleys, only to find the water suddenly diverting around an invisible mountain. These anomalous lensing effects are the telltale signs of what astronomers call substructure, small, dense clumps of dark matter that are nested within the larger halo of the cluster. Our simulations predict that dark matter halos should be filled with thousands of these smaller subhalos, the very same ones that were supposed to host the missing satellite galaxies. The anomalous lensing could be the first direct, albeit indirect, evidence that these subhalos are indeed there. They are massive enough to significantly warp light, but they are so devoid of stars that they remain completely dark, invisible to any telescope except through their subtle gravitational footprint on distant starlight. However, there is a far more radical interpretation of these strange lensing patterns. A small but dedicated group of physicists argues that these anomalies are not evidence for dark matter clumps, but are instead proof that our theory of gravity itself is flawed. Modified Newtonian dynamics, or MUND, proposes that on very large scales and in regimes of extremely weak gravity, like the outskirts of galaxies and clusters, gravity behaves differently than Einstein predicted. It becomes stronger than expected, producing effects that mimic the presence of invisible matter. Proponents of MUND point to these specific lensing anomalies in Virgo as a potential smoking gun. They create their own models based on a modified law of gravity without any dark matter at all, and in some cases, they can reproduce the strange distortions more accurately than the standard model can. For them, the light isn't bending around invisible clumps. It is simply following the rules of a new, deeper law of physics that we have not yet fully grasped. This places astronomers in a fascinating dilemma. Each anomalous arc is a silent witness, but its testimony is ambiguous. Is it pointing to the cold, dark presence of invisible mass clumps, finally confirming a key prediction of our standard model? Or is it revealing the subtle breakdown of general relativity itself, beckoning us toward a scientific revolution that would dwarf the discovery of dark matter? The answer lies in collecting more of these cosmic fingerprints, with every new lensing system studied in Virgo, and with the upcoming power of the James Webb Space Telescope to see them in unprecedented detail, we get closer to deciphering this gravitational code. The warped light of these distant galaxies is more than a pretty picture. It is a profound diagnostic tool, probing the very nature of mass, gravity, and reality on the largest scales. Now we encounter a mystery that strikes at the very heart of the cluster, a puzzle of cosmic thermodynamics that pits the irresistible force of a supermassive black hole against the seemingly immovable object of a cool, dense cloud of gas. This is the Virgo Cluster's cool core riddle. Imagine a colossal, swirling whirlpool of plasma, heated to tens of millions of degrees by the sheer violence of galactic collisions and the fury of active black holes. This is the intracluster medium we've come to know. Logic dictates that the very center of this maelstrom, the deepest part of the gravitational well where matter is most densely packed and energy is most concentrated, should be the hottest place of all. Yet, when we point our most powerful X-ray telescopes like Chandra and XMM Newton at the core of the Virgo cluster, that's not what we see at all. The data reveals a stunning paradox. Right at the very center, surrounding the galaxy M87, the gas is significantly cooler and denser than its surroundings. In the temperature maps, this region shows up as a splash of blue and purple amidst a fiery sea of red and yellow. A calm and surprisingly chilly eye at the center of a billion-year storm. This cool core presents a profound challenge to our understanding of how clusters evolve. The hot gas in the cluster should be constantly losing energy. As it radiates away its heat in the form of X-rays, it should naturally cool down. As it cools, it should contract, becoming denser and falling inward toward the cluster's center in what theorists call a cooling flow. In an unimpeded universe, this process would be a runaway train. Vast rivers of cold gas would stream into the cluster's core, providing an unimaginable fuel supply that would trigger an epic burst of star formation, potentially creating millions of new suns every year and building a galaxy of incomprehensible size. Our telescopes should see a central galaxy glittering with the blue light of countless young stellar nurseries, but we don't. The star formation rates in the heart of Virgo are a mere trickle compared to what this theoretical cooling flow would produce. Something is acting as a cosmic thermostat, preventing the gas from cooling catastrophically and shutting down this starbirth frenzy. For decades, the leading theory for this balancing act has been Aegean feedback. The supermassive black hole at the center of M87 is the perfect candidate for this regulatory role. The theory is beautifully elegant. As the hot gas cools and begins to flow inward, some of it inevitably feeds the black hole. This accretion process powers the colossal jets and outbursts we see. These jets then blast back into the surrounding gas, like a colossal engine firing its exhaust into a fog. This injection of tremendous energy stirs up the gas, shocks it, and reheats it, effectively shutting off its own fuel supply. It's a self-regulating feedback loop, a cycle of feeding and feedback that maintains the core in a precarious, warm state too hot to collapse into a deluge of stars, but cool enough to remain dense and detectable. This model has become a cornerstone of modern astrophysics, explaining not just cluster cores but the growth of all massive galaxies. However, when scientists try to simulate this exact process in the Virgo cluster, they run into a wall. Their most sophisticated computer models, which include the physics of gas cooling, gravity, and black hole feedback, consistently fail to replicate the delicate balance we actually observe. The simulations are prone to extreme outcomes. In some virtual runs, the feedback is too weak. The cooling flow wins, and the simulation creates a central galaxy that is far too bright and massive, with star formation rates that dwarf anything in the real universe. In other runs, the feedback is too strong. The black hole's outbursts are so violent that they blow all of the gas out of the cluster core entirely, leaving behind a hot, diffuse, and almost empty cavity, the opposite of the cool, dense core we see in Virgo. Getting the simulation to consistently produce a stable, long-lived cool core like the one in Virgo has proven incredibly difficult. The models can't seem to find the sweet spot, the precise tuning of energy injection that matches nature's own delicate handiwork. This struggle suggests that our understanding of the feedback mechanism itself is incomplete. We might be missing key pieces of the physics. perhaps the energy from the black hole isn't deposited in the smooth, spherical way the simulations assume. Maybe it is channeled more efficiently through specific, narrow jets or converted into forms of energy we don't fully account for, like sound waves or turbulence, which could heat the gas in a more gentle and distributed manner. Alternatively, other processes might be assisting with the heating. Could the gentle stirring of gas from smaller galactic mergers or the gradual release of energy from cosmic rays also play a vital role in maintaining this balance? The cool core of the Virgo cluster is not a static object. It is a dynamic equilibrium, the product of a billion-year tug of war between forces of creation and destruction. Its very existence tells us that our models of black hole physics and plasma heating are close, but not yet perfect. Each new, detailed temperature map from an X-ray observatory provides a more precise benchmark, a clearer picture of the end result that our theories must strive to explain. This serene, cool pocket at the center of a cosmic firestorm is a silent testament to a complex and beautiful dance between a monster and its meal, a dance we are still learning the steps to. But just as we ponder the slow, thermodynamic dance at the cluster's heart, the universe reminds us that it is also capable of unleashing bursts of energy so sudden and so violent they defy comprehension, events that pack the power of hundreds of millions of suns into a fleeting thousandth of a second. This brings us to one of the most electrifying mysteries in modern astronomy: fast radio bursts, or FRB. For years, these incredible bursts of radio waves seem to come from the distant, ancient universe, their incredible distances making them difficult to study. But then, astronomers began to pinpoint a number of these enigmatic signals not from the far cosmic horizon, but from right here in our own supercluster, with several traced directly to galaxies within the Virgo cluster itself. The localization of these events to our cosmic backyard has transformed them from curious anomalies into accessible and profoundly puzzling subjects of intense scrutiny. Detecting an FRB is a feat of modern engineering and patience. Unlike the steady glow of a star or the predictable pulse of a pulsar, an FRB is a singular, transient event. To catch one, radio astronomers use massive dishes and sophisticated digital backends that continuously scan the sky, recording enormous amounts of data. The key signature is a signal that appears suddenly in the data stream, a brilliant spike of radio emission that typically lasts just a few milliseconds. But the most important clue is something called a dispersion measure. As the burst travels through the sparse sea of electrons in intergalactic space, higher frequency radio waves travel slightly faster than lower frequency waves. This causes the burst to arrive at our telescopes as a descending chirp. The high notes hit first, followed by the lower ones. By measuring the precise delay between the highest and lowest frequencies, scientists can calculate the total amount of material the signal has passed through, providing a rough estimate of its distance. When that calculation points to a source within the Virgo Supercluster, the hunt for a host galaxy begins. Using a network of radio telescopes across the globe in a technique called very long baseline interferometry, astronomers can achieve incredibly precise triangulation, sometimes pinpointing the origin of a burst to a specific galaxy or even a specific region within a galaxy. The sheer energy involved is staggering. A typical FRB releases more energy in a millisecond than our Sun does in 80 years. Concentrating that much power into such an infinitesimally short window of time requires an engine of almost unimaginable ferocity. The debate over what that engine could be is where the mystery truly deepens, and the leading theories range from the exotic to the truly bizarre. The most favored explanation points to magnetars, a type of neutron star with a magnetic field so powerful it could erase a credit card from halfway to the moon. A starquake on the surface of such an object, or a sudden rearrangement of its immensely powerful magnetic field, could theoretically unleash a cataclysmic burst of energy that we would see as an FRB. This theory gained significant support when a magnetar within our own Milky Way galaxy was observed producing a radio burst that, while much weaker, shared many characteristics with the extragalactic FRBs. However, not all FRBs are created equal. Some burst once and are never heard from again, while others, the repeating FRBs, fire off multiple signals from the same location, sometimes in unpredictable patterns. This simple fact of repetition is a monumental clue, as it immediately rules out any cataclysmic, one-time-only event like the collision and mutual destruction of two neutron stars. A repeater cannot be a cosmic explosion. It must be an object that survives its own outburst, an engine that can fire multiple times. This has led to other compelling ideas, such as a neutron star in a highly eccentric orbit around a black hole or another neutron star. On each close pass, immense tidal forces could rip material from the star's surface, triggering powerful bursts of emission. Or perhaps the answer lies with an active galactic nucleus, where a supermassive black hole's accretion disk experiences periodic instabilities that launch incredibly powerful shock waves. Yet, for some scientists, even these extreme astrophysical scenarios feel insufficient. The incredible brevity and brightness of the signals have prompted a minority to consider more exotic possibilities rooted in fundamental physics. Could FRBs be the signature of cosmic strings theoretical, one-dimensional defects in the fabric of spacetime snapping and releasing vast amounts of energy? Or might they be evidence of powerful beams from advanced extraterrestrial civilizations, a concept that, while highly speculative, is not formally ruled out by the data? While these ideas are far less likely than natural astrophysical origins, their very consideration highlights just how perplexing these millisecond miracles truly are. The dynamic spectra of these bursts, colorful plots of intensity versus frequency and time, are the primary data that astronomers scrutinize. Each descending sweep of color tells the story of the burst's journey through the cosmos. But sometimes the story has strange twists. Fine substructure within the burst, like multiple subbursts drifting downward in frequency, or sudden nulls in the signal, suggest an incredibly complex emission process happening near the source itself. Animations that illustrate this often show a wave of energy propagating outward from a central, compact object, its different frequencies spreading out as it travels for millions of years through the tenuous plasma of intergalactic space before finally being captured in a split second of data on Earth. Each localized Virgo FRB provides a much clearer, brighter signal for this kind of detailed forensic analysis, offering our best chance to finally understand the physics behind these cosmic lightning strikes. Their relative proximity turns them from faint, mysterious chirps from the edge of time into loud, clear messages from our local universe, each one demanding an explanation for the incredible violence lurking within the seemingly serene galaxies of our supercluster. Yet as we observe the frenetic energy of fast radio bursts and the complex interplay within cluster cores, we must step back to view the Virgo cluster as a whole, not as a random collection of islands, but as a carefully organized archipelago where the very shape and structure of each galaxy tells a story written by its environment. This brings us to one of the most fundamental puzzles in large-scale cosmic structure, the galaxy morphology-density relation, and the curious ways it seems to break down within Virgo. For decades, a clear and elegant rule has guided our understanding. The shape of a galaxy is profoundly influenced by its neighborhood. In the sparse, quiet suburbs of the cosmic web, the low-density voids and field spiral galaxies dominate. Their majestic, star-forming disks rotate peacefully, largely undisturbed. But in the dense, bustling downtown core of a massive cluster, a different galactic citizenry takes over, the smooth, red, and generally round elliptical galaxies. The theory is that the violent, crowded environment of a cluster literally beats the spirals into a new shape, transforming them through a series of dramatic and destructive processes. This rule holds true in a general sense, but when astronomers create detailed morphology maps of the Virgo cluster, charts that color-code each galaxy by its type, and compare them to the predicted density maps from sophisticated environmental simulations, the match is far from perfect. There are glaring anomalies, pockets of dense intracluster medium where every spiral should have been eradicated, sometimes harbor a few resilient disk galaxies spinning on against all odds. Conversely, some regions on the quieter outskirts of the cluster host surprisingly large populations of dead, elliptical galaxies that should, by all rights, still be vibrant spirals. The universe, it seems, is not following its own rulebook as closely as we expected, and Virgo is the perfect laboratory to find out why. The primary suspects in this galactic transformation are threefold, each a different flavor of cosmic violence. The most dramatic is merger-driven transformation, when two spiral galaxies of roughly equal size collide in a slow, gravitational dance. Their beautiful disks are shredded beyond recognition. The orderly rotational motion of the stars is scrambled into random orbits. Gas is compressed and drained in a ferocious burst of star formation, and the result is a new, featureless elliptical galaxy. This is a relatively fast and efficient way to erase a spiral's identity. The second process is galaxy harassment. In the crowded core of the cluster, a spiral doesn't need to suffer a direct hit to be affected. The cumulative effect of countless high-speed, close encounters with other galaxies can gently perturb it over time. These gravitational nudges can pump energy into the disk, puffing it up, stirring its gas, and gradually morphing it into a more spheroidal, lenticular galaxy, a disk without the spiral arms, a transitional form on the way to becoming a full elliptical. The third and perhaps most efficient method is ram pressure stripping, which we've seen in action with NGC 4388. This process doesn't necessarily change the shape of the galaxy's stellar body immediately. Instead, it surgically removes its lifeblood, the cold gas needed to form new stars. The spiral arms, fed by star formation, fade away over time, leaving behind a so-called anemic spiral, or transforming it into a passive, red and dead disk. So why doesn't this always work as predicted in Virgo? The answer lies in the cluster's complex and layered history. Unlike some older, more relaxed clusters, Virgo is still assembling itself. It is not a single, monolithic structure, but a dynamic confluence of smaller groups and subclusters falling in at different times and from different directions. This means the environmental density is not a smooth gradient, it's a patchwork. A galaxy falling into the cluster on a slow, tangential orbit might spend billions of years cruising through the low-density outskirts, experiencing very little harassment or pressure, and thus retaining its spiral structure far longer than a model would predict. Another galaxy might have fallen into a dense subcluster early on, been transformed into an elliptical, and then that entire group later merged with the main Virgo cluster, depositing its already dead galaxies right in the midst of what should be a spiral-rich region. The morphology map we see today is not a snapshot of a single environmental process, but a palimpsest, a layered historical record of every merger, every infall event, and every orbit that every galaxy has ever taken. The anomalies are not errors, they are clues to this rich history. A lone spiral surviving in a dense core might be a recent arrival, still holding onto its gas as it plunges in for the first time. A group of ellipticals on the outskirts might be a fossil group, the ancient core of a structure that was consumed long ago. By reading these patterns, astronomers can work backwards to reconstruct the cluster's assembly, using the shapes of galaxies as fossils to trace a history of cosmic violence that unfolded over billions of years. Yet as we map the grand patterns of galaxy shapes and motions, our investigation takes a turn toward one of the most contentious and mind-bending controversies in all of modern cosmology, a claim that strikes at the very method we use to measure the universe itself. This is the puzzle of redshift quantization, our audacious proposal that the redshifts of galaxies, particularly within our local supercluster, are not smoothly distributed as everyone assumes, but instead appear to prefer specific, evenly spaced values like a cosmic energy ladder. If true, this wouldn't just be a curiosity. It would imply that a fundamental pillar of our understanding of the expanding universe is somehow flawed or incomplete. To grasp the sheer radical nature of this idea, we must first recall what redshift is and how we use it. When a galaxy moves away from us, the wavelength of its light is stretched, shifting its spectral lines toward the red end of the spectrum. This Doppler-like effect is the primary way we measure a galaxy's velocity. Since the late 1920s, we've understood that the further away a galaxy is, the faster it appears to be receding from us due to the overall expansion of the universe, a relationship encapsulated in Hubble's law. This cosmological redshift is the very foundation of the cosmic distance ladder. We measure the redshift, we plug it into Hubble's law, and we get a distance. It's a process so fundamental that it's treated as an unquestionable rule. The controversy began when a few astronomers, most notably William Tift, began analyzing the redshifts of galaxies with incredibly high precision. Instead of simply looking at the overall recession velocity, they looked at the finer details, specifically the component of motion that remains after you subtract out the smooth Hubble flow, the peculiar velocity that shows how a galaxy is moving within its local gravitational field. When Tift and later researchers like Holton Arp plotted histograms of these corrected redshifts for galaxies in the Virgo Cluster and other nearby groups, they claimed to see something astonishing. The data points didn't fill the graph like a smooth, random scatter. Instead, they appeared to clump at specific preferred values with the redshift seemingly quantized in regular steps. The most commonly cited step size is around 72 kilometers per second, meaning galaxies seem to have recession velocities that were multiples of this number, as if the universe were somehow ticking in discrete intervals rather than a smooth, continuous flow. The implications of such a finding are nothing short of revolutionary. Redshift quantization, if real, would suggest that redshifts are not purely a measure of velocity and distance. They might instead be an intrinsic property of galaxies, perhaps related to their age or some other fundamental physical characteristic we don't yet understand. Proponents of this view point to these patterns as evidence that the cosmological redshift we measure is not entirely due to the expansion of the universe. This would mean that many galaxies, especially those with these quantized values, are not as distant as we think they are, fundamentally altering our cosmic maps and our estimate of the size and age of the universe. Some have even suggested it could be a signature of entirely new physics, a wave-like property of the cosmos on a grand scale. Unsurprisingly, the mainstream astronomical community has greeted these claims with profound skepticism, and the debate has been heated for decades. The primary counter-argument is a simple one: sampling bias and statistical fluke. Critics argue that the patterns disappear when you use larger, more complete samples of galaxies. The apparent peaks in the redshift histograms, they say, are an illusion created by selectively analyzing certain groups of galaxies while ignoring others. It's like hearing a melody in random noise. Your brain is pattern matching, but the pattern isn't really there. Furthermore, the complex gravitational environment of a cluster like Virgo creates all sorts of peculiar velocities as galaxies swarm and interact. Isolating a single, clean signal from this dynamical chaos is an immense challenge, and many argue that the quantization signals vanish when more sophisticated models of the cluster's gravitational potential are used to calculate the true peculiar motions. The controversy remains unresolved, a testament to the immense difficulty of doing science at the very edge of detection. It pits a small group of researchers who believe they have found a profound anomaly against a vast majority who believe the anomaly is a phantom born of wishful thinking and imperfect data. The heart of the problem is that the claimed effect is tiny, sitting right at the limit of the measurement precision of our best instruments. Each new, more precise redshift survey, like the Sloan Digital Sky Survey, provides a new battleground. Proponents sift through the new data, claiming to find fresh evidence for the peaks in the histograms, while skeptics use the same data to argue the case is even weaker. This ongoing, decades-long debate is a powerful example of how science wrestles with extraordinary claims. It showcases the rigorous, often slow process required to distinguish a true signal from noise, a process that demands independent verification and relentless questioning. Whether a profound discovery or a persistent mirage, the redshift quantization controversy forces us to continually re-examine our most basic assumptions about the cosmos. But just as we grapple with the grand motions of galaxies and the fleeting signals from the depths of space, our investigation turns to a more subtle mystery, one written in the very elemental composition of the cluster itself. To truly understand the history of the Virgo cluster, we must become cosmic chemists analyzing the ingredients of the vast fog of hot gas that fills the space between its galaxies. This intracluster medium is not a pristine relic of the Big Bang. It is a polluted record of billions of years of stellar life and death, enriched by the ashes of countless supernovae. Yet, when we read this chemical record with our most powerful X-ray telescopes, we find a story that doesn't quite match the one we thought we knew, revealing unexpected ratios of elements that point to a more complex and violent history. The primary tool for this forensic work is X-ray spectroscopy. Instruments aboard observatories like Chandra and XMM Newton don't just take pictures, they act as cosmic prisms, splitting the X-ray light from the hot gas into a detailed spectrum. Within this spectrum are specific, sharp dips and peaks absorption and emission lines that act as unique fingerprints for every chemical element present. The depth and width of these lines tell us not only which elements are there, but also their relative amounts and the temperature of the gas therein. By staring at the Virgo cluster for long periods, astronomers can build up incredibly detailed abundance maps, creating a periodic table of the cosmos that shows how elements like iron, oxygen, silicon, and neon are distributed across millions of light years. These maps reveal a profound and puzzling anomaly. According to our well-established models of stellar nucleosynthesis, the process by which stars forge new elements, we expect a certain predictable ratio between elements. For instance, core collapse supernova, the spectacular explosions of massive young stars, are prolific factories for alpha elements like oxygen, neon, and magnesium. They blast these lighter elements out into space with tremendous force. In contrast, Type Ia supernova, which involve the thermonuclear detonation of a white dwarf star, are the universe's primary producers of iron and nickel. They create and distribute these heavier elements. In a typical galaxy, the balance between these two types of supernova over time creates a specific chemical signature. But the intracluster gas in Virgo tells a different story. The ratio of iron to oxygen is far higher than our standard models predict. There is simply too much iron floating between the galaxies. It's as if the cluster's history was dominated by an overabundance of Type Ia supernova relative to the core collapse variety. This is deeply confusing because core collapse supernova should be more common, especially in the early universe when massive stars were plentiful. So where did all this extra iron come from? One compelling theory points directly to the active galactic nuclei at the hearts of many Virgo galaxies. The powerful outflows and jets from these supermassive black holes could act as enormous conveyor belts, not just heating gas but also transporting it. These AGN-driven winds might be preferentially ejecting iron-rich material from the central regions of galaxies, where Type Ia supernova are more common, and hurling it out into the intracluster medium. This process would effectively mine the galaxies of their iron, and dump it into the common pool of the cluster, enriching it beyond what would be expected from supernova alone. Another, more intriguing possibility involves the very first stars. The earliest stellar generation, known as population 3 stars, are thought to have been monstrously large and to have lived fast and died young in tremendous supernova. Theoretical models suggest these primordial explosions could have had a different nucleosynthetic yield than later supernova, potentially producing a different mix of elements. If the Virgo cluster formed early and rapidly, it could have locked away a significant amount of this primordial enrichment in its intracluster gas, a fossil signature from the dawn of star formation that subtly alters the overall chemical balance we see today. The implications of this chemical puzzle reach far beyond mere accounting. The abundance of elements directly influences the cooling rate of the intracluster gas. Iron, in particular, has atomic properties that make it extremely efficient at radiating away heat. An overabundance of iron could therefore significantly accelerate the cooling of the gas in the cluster core, potentially fueling the very cooling flows that the Aegean struggle to suppress. This creates a fascinating feedback loop. Aegean may be responsible for dumping extra iron into the gas, which then makes the gas cool faster, which in turn provides more fuel for the Aegean, prompting more outbursts. The unusual chemical abundances we detect are not just a static observation. They are a dynamic and critical part of the cluster's ongoing evolution, a hidden variable in the equation of how galaxy clusters live and die. This elemental enigma proves that to understand the cosmos, we must not only map its mass and energy, but also read its complex chemical history, a story written in the faint X-ray glow of atoms forged in the hearts of stars and distributed by the most violent events in the universe. These stellar streams are more than just phantom limbs. They are the literal backbone of the cluster's formation history, a fossilized record of its violent assembly. To find them, astronomers must become masters of cosmic subtraction. Using ultra-sensitive instruments on telescopes like the Subaru telescope and the Canada-France-Hawaii telescope, they take incredibly deep, wide-field images of the Virgo core. They then employ sophisticated software to digitally remove the light from every known star and galaxy, a process that peels back the bright foreground to reveal the faint underlying tapestry. What emerges is stunning, vast, river-like structures of stars, some stretching for hundreds of thousands of light years, weaving between the brilliant galaxies like cosmic waterways. The most famous of these is the immense stream entwined around the giant galaxy M87 itself, a colossal loop of stars that tells a story of a dramatic encounter billions of years in the past. The very existence of these streams confirms the hierarchical model of structure formation, the idea that large galaxies grow by consuming smaller ones. As a dwarf galaxy ventures too close to a giant like M87, the immense and uneven gravitational pull stretches it, first into a tidal tail and then into a long, thin stream that eventually disperses into the halo. It's a process we see in simulations, a fundamental rule of galactic ecology. Yet, when we compare the precise orbits, densities, and morphologies of the real streams in Virgo to those in our most sophisticated virtual universes, we find puzzling mismatches that suggest our simulations are still missing a crucial piece of physics. The real streams appear more coherent and longer-lived than they should be. Their stars remain gravitationally bound to each other in these delicate structures for far longer than the models predict. According to the simulations, the relentless gravitational tides from the cluster and the giant galaxy at its heart should have shredded these streams into a smooth, indistinct halo of starlight long ago. The fact that they persist as distinct, traceable rivers means something is helping them hold together. This unexpected coherence points directly to the hidden hand of dark matter. The leading theory is that these disrupted dwarf galaxies were not just loose collections of stars. They were embedded within their own dense, massive halos of dark matter. This dark matter acts as a kind of gravitational glue. Even as the visible stars are pulled away into a stream, the dark matter halo is stretched along with them, its unseen mass providing a stabilizing skeleton that helps the stellar stream maintain its structure against the disruptive tidal forces of the cluster. The streams we see are therefore not just ribbons of stars, they are ribbons of stars still shrouded in their own invisible, protective cocoons of dark matter. By carefully mapping the exact shape and width of a stream, astronomers can actually work backwards to estimate the amount and distribution of this dark matter, turning these faint features into direct probes of the invisible universe. However, the mysteries only deepen when we examine specific streams in detail. Take the complex system of loops and shells around M87. This structure is not a single stream but a layered palimpsest, the result of multiple accretion events over time. By studying the subtle differences in the color and metallicity, the abundance of elements heavier than hydrogen and helium of the stars in different parts of the structure, astronomers can perform a kind of cosmic archaeology. Stars from different dwarf galaxies will have unique chemical signatures forged in their original stellar populations. These studies reveal that M87 has consumed not just one, but a whole series of small galaxies, each event leaving a distinct filament in the stellar web. The enigma is that the orbits of these streams, as traced by their current positions, are often difficult to reconcile with the cluster's gravitational field as we understand it. They seem to follow paths that imply a past history of the cluster that is more chaotic and dynamic than our smooth models suggest, perhaps involving a major merger with another large galaxy that shook the entire gravitational foundation of Virgo and sent these streams on unexpected trajectories. This brings us to the most profound implication of these stellar enigmas, the possibility of a slingshot. Some of the most extreme stellar streams discovered in other parts of the sky, like the stunning giant stream in the Andromeda galaxy, appear to have been flung into their vast orbits not by a single galaxy, but by the combined gravitational kick of two galaxies orbiting each other. This three-body interaction can catapult a dwarf galaxy or a globular cluster into a wildly elongated orbit, stretching it into a stream that can loop around the entire galactic system. While not yet confirmed in Virgo, the presence of several massive galaxies like M86 and M84 in relative proximity makes such a dynamic slingshot effect a compelling possibility for explaining some of the most bizarre and extended stream orbits we observe. These stellar rivers are therefore more than just relics. They are the ultimate record of the cluster's most violent gravitational interactions, a history written in starlight that we are only just beginning to learn how to read. Now, as we trace the ghostly streams of stars and map the silent pull of dark matter, our investigation into the Virgo Supercluster's mysteries takes a turn toward the infinitesimally small toward particles traveling at nearly the speed of light that carry with them the signature of the most violent events in the universe. We are entering the realm of cosmic rays, and within the data collected from these high-energy messengers, there is a signal from the direction of Virgo that defies all our expectations, presenting a puzzle that challenges our understanding of physics itself. Cosmic rays are not rays of light. They are actual particles, mostly protons and atomic nuclei, that have been accelerated to breathtaking energies. They are the universe's natural particle accelerators, but operating on a scale that makes our largest human-built colliders seem trivial. To detect them, scientists build enormous observatories like the Pierre Auger Observatory in Argentina, which uses an array of over 1,600 water tanks spread across 3,000 square kilometers. When a high-energy cosmic ray slams into the top of our atmosphere, it creates a massive shower of secondary particles. These particles spread out, traveling at nearly the speed of light, and when they hit the water in the detectors, they produce a tiny flash of light called Cherenkov radiation. By measuring the timing and intensity of these flashes across the vast array, scientists can work backwards to calculate the original particle's energy, its charge, and most importantly, the direction from which it came. For the most part, the data aligns with our theories. We know that cosmic rays are accelerated by powerful shock waves, like those from supernova remnants within our own galaxy. These expanding shells of debris act like massive particle traps, with magnetic fields bouncing charged particles back and forth across the shock front, boosting their energy with each pass. This process, called diffusive shock acceleration, is a beautifully efficient engine, and it explains the origin of the vast majority of cosmic rays we detect. However, a small but significant fraction of the highest energy events tell a different story. These are the ultra-high-energy cosmic rays, particles with energies millions of times greater than those produced in the Large Hadron Collider. When scientists at the Pierre Auger Observatory plotted the arrival directions of these rare, exceptional events, they noticed a curious and persistent anisotropy, a slight but statistically significant clustering of events coming from a broad region of the sky that includes the heart of the Virgo Supercluster. This alone is a clue. It suggests that the most powerful particle accelerators in the local universe are located in that direction. The real mystery, however, lies not just in their origin, but in their composition. As these ultra-high-energy particles travel through space, they interact with the photons of the cosmic microwave background, the afterglow of the Big Bang. This interaction creates a theoretical limit on how far they can travel, known as the GZK cutoff. For the very highest energy protons, this distance is relatively short on a cosmic scale. The fact that we see them at all means they must come from relatively nearby sources within our local supercluster, like Virgo. But when astronomers analyze the data to determine what type of nuclei these particles are, they find a perplexing mix. Some events suggest light nuclei, like protons, while others indicate much heavier elements, like iron nuclei. This is deeply confusing because the known acceleration mechanisms struggle with heavy nuclei. It is vastly more difficult for a shock wave to accelerate a heavy iron nucleus to the same incredible speed as a lightweight proton. The fact that we see both suggests that either our understanding of particle acceleration is fundamentally flawed, or that there is more than one type of accelerator at work in Virgo, each operating by a different set of rules. So what cosmic engines in Virgo could be capable of such feats? One prime suspect is the relativistic jet screaming from the supermassive black hole at the center of Messier 87. The magnetic fields and intense shocks within such a jet are perfect candidates for accelerating particles to these phenomenal energies. Another possibility is a population of hidden, yet unidentified supernova remnants within the cluster's many galaxies, perhaps occurring in environments so extreme that they far surpass the power of any supernova we've studied in our own galaxy. Then there is the most speculative but most thrilling possibility that these anomalous cosmic rays are not from conventional accelerators at all, but are the direct products of dark matter annihilation or decay. If dark matter is made of theoretical super-heavy particles, their mutual destruction could release a burst of energy that creates standard model particles, including protons and heavy nuclei, which would then travel to Earth as cosmic rays. The Virgo cluster, being immensely dense with dark matter, would be a prime location for such a process to occur. The anomalous energy spectrum and composition we detect could be the literal fingerprint of dark matter particles meeting their end. Each high-energy particle that strikes a detector in the Argentine desert is a messenger, and its journey millions of light years to reach us may have begun not in a stellar explosion, but in the silent, invisible decay of the universe's most mysterious substance. While we've charted the currents within the Virgo cluster and the broader supercluster, our journey now pulls us toward a far grander and more mysterious gravitational force, one whose influence shapes the motion of not just Virgo, but of our entire local universe. This is the enigmatic Great Attractor, a colossal concentration of mass that lies in the direction of the constellations Norma and Centaurus, pulling millions of galaxies, including our own, toward it with an irresistible gravitational tug. Its existence was first inferred not by what we could see, but by what we could measure. A startling deviation in the universal expansion pattern that suggested a vast, unseen river of galaxies was all flowing in the same direction. To visualize this, astronomers create sophisticated velocity flow maps. These are not simple pictures, they are complex data visualizations that plot the peculiar velocities of galaxies, their real motion through space after the smooth, predictable expansion of the universe has been subtracted out. Imagine a map of the world's oceans where the arrows don't show the water itself, but the powerful underlying currents that drive it. When such a map is made for our local universe, a stunning pattern emerges. Instead of random motion, the arrows reveal a coherent stream. Galaxies across a vast volume of space, including the entirety of the Virgo Supercluster, are all moving in a consistent direction toward a point roughly 250 million light-years away. This is the gravitational signature of the Great Attractor, a downpour of galaxies on a cosmic scale with Virgo caught in the current. But what exactly is pulling us? This is where the mystery truly deepens. When astronomers first pointed their optical telescopes toward that region of the sky, they found their view obscured by the dense plane of our own Milky Way galaxy, a zone known as the zone of avoidance, where dust and stars block our sight of the distant universe. It was like trying to find the source of a mighty river while standing in a dense fog bank. The initial suspicion was that the Great Attractor must be an unimaginably massive, yet hidden cluster of galaxies. Subsequent observations, however, have painted a more complex picture. We now know that part of this motion is indeed caused by a known, massive concentration of mass, the Norma cluster, also known as SEO 3626. This is a rich cluster, a gravitational anchor in its own right. But here's the puzzle. When astronomers add up the mass of the Norma cluster and all other visible structures in that direction, it still isn't enough to account for the full strength of the pull we feel. The observed motion is simply too great for the amount of visible matter we can detect. This discrepancy has led to two compelling and not mutually exclusive explanations. The first is that the Great Attractor is not a single object, but a massive confluence of several rich clusters and superclusters, including the Norma cluster and the even larger Shapley supercluster that lies beyond it. In this view, the Great Attractor is a gravitational nexus, a grand focal point where the largest scale filaments of the cosmic web intersect. The pull we feel is the combined gravity of this entire immense structure, a gravitational watershed on a supercluster scale. The second, more radical possibility is that there is still a significant component of unseen mass, either in the form of dark matter distributed in a way we haven't mapped, or perhaps even more exotic large-scale structures that remain hidden behind the Milky Way's veil. The impact on the Virgo Supercluster is profound and multifaceted. This external pull doesn't just give Virgo a gentle nudge, it fundamentally influences its dynamics and evolution. The gravitational tide from the Great Attractor adds a directional component to the chaotic orbital motions of galaxies within Virgo, potentially influencing how they interact and merge. It contributes to the overall shear forces that can strip gas from galaxies and affect star formation rates. On the largest scale, it dictates the ultimate trajectory of the entire supercluster within the cosmic flow, pulling it toward a destiny of a future merger with other massive structures in this gravitational basin. The Great Attractor is a reminder that no structure in the universe is an island. Even something as vast as the Virgo Supercluster is itself a mere satellite, caught in the gravitational wake of a far greater and more mysterious cosmic power. Yet for all the violence of stellar explosions and the eerie calm of fading tidal events, the most perplexing transient signals from Virgo are those that defy any known classification. Monitoring programs have occasionally captured brief, brilliant flares of light that appear and vanish without any of the expected afterglow or lingering emission at other wavelengths. These are not supernova, their light curves are all wrong, rising and falling in hours or days instead of weeks. They are not tidal disruption events. There is no corresponding supermassive black hole at the location. They are ghost signals, one-off events that blaze into existence in the heart of a galaxy or even in the seemingly empty space between them, and then are gone, leaving behind only a pixelated question mark on a digital sensor. Some astronomers speculate these could be the signatures of entirely new classes of catastrophe, perhaps the merger of two ultra-dense objects like neutron stars and white dwarfs in a previously unobserved configuration, or the sudden collapse of a supermassive star directly into a black hole without a supernova, a so-called unnova. Others wonder if we are seeing the effects of rare gravitational lensing events, where the light from a distant flare is momentarily magnified by an invisible foreground object, creating a fleeting spike of brightness that is actually a cosmic mirage. Each unclassified flare is a reminder that our inventory of cosmic violence is still incomplete, and that the galaxies of the Virgo Cluster, for all their proximity, still hold the capacity to surprise us with entirely new forms of ephemeral brilliance. Yet, even as we trace the grand currents shaped by the Great Attractor and the fleeting brilliance of unexplained flares, we arrive at a mystery that strikes at the very heart of modern cosmology, a fundamental disagreement over the rate at which the universe itself is expanding. This is the Hubble constant tension, and observations of the Virgo Cluster are playing a pivotal role in this high-stakes debate, forcing astronomers to question whether we might need new physics to reconcile two utterly irreconcilable views of our cosmic reality. The Hubble constant, known as H0, is arguably the most important number in cosmology. It quantifies the present-day expansion rate of the universe, telling us how fast a galaxy is receding from us for every megaparsec of distance. Measuring it accurately is like calibrating the ultimate cosmic speedometer, and it's crucial for determining the age, size, and ultimate fate of everything we see. For decades, the quest to pin down this number has proceeded along two distinct paths, often called the distance ladder method and the early universe method. It's the stark, growing discrepancy between the results from these two approaches that has ignited the current crisis. The first path relies on building a cosmic distance ladder, a step-by-step process that starts right here in our galactic neighborhood. Astronomers use incredibly reliable celestial yardsticks, with Cepheid variable stars being the most famous and crucial first rung. These stars pulsate with a regularity that is directly tied to their intrinsic brightness. By measuring their pulsation period from the ground, astronomers know their true luminosity, comparing this known brightness to their apparent, dimmed brightness as seen from Earth gives a precise distance. The next rung often involves Type Ia supernova, the spectacular thermonuclear explosions of white dwarf stars. These events are so uniform in their peak brightness that they are known as standard candles. By finding these supernovae in galaxies that also contain Cepheid variables, scientists can calibrate the supernova's true power. Once calibrated, these supernovae are so brilliant they can be seen in galaxies far across the universe, allowing astronomers to extend the distance ladder all the way out to the Virgo Cluster and beyond. When they measure the redshift and distance to these far-flung galaxies, they can calculate H0. This local measurement, heavily reliant on Virgo and similar clusters, consistently gives a value of around 73 kilometers per second per megaparsec. The second path takes a completely different approach, looking not at nearby galaxies but at the faint afterglow of the Big Bang itself, the cosmic microwave background. Satellite missions like Planck have mapped this relic radiation in exquisite detail. The tiny temperature fluctuations in this map are a frozen record of the universe's infancy. By applying our very successful model of the universe's composition and evolution, the lambda-cold dark matter model, to these primordial ripples, cosmologists can predict how the universe should have expanded to reach its present state. This early universe method yields a Hubble constant value of around 67 kilometers per second per megaparsec. The difference seems small, just a few digits, but the statistical significance is enormous. These two values are separated by a gulf that cannot be explained by measurement error. They are fundamentally, unequivocally incompatible. It's as if you calculated the speed of a car by measuring its engine's revolutions, and then again by timing it between 2 mile markers, and got two wildly different answers that both claim to be correct. This is the Hubble tension, and it suggests a profound crack in our standard model of cosmology. This is where Virgo becomes absolutely essential, because it is the crucial crossroads where these two methods meet and conflict. The cluster is close enough for us to use both Cepheids and another powerful local method called the tip of the red giant branch, or TRGB, to measure distances. TRGB uses the fact that all old populations of stars have a distinct cutoff point in their brightness, the point at which the most massive red giant stars ignite helium in their cores. This tip has a very predictable luminosity, making it another excellent standard candle. Intriguingly, when some teams use the TRGB method to calibrate the distance to Virgo and other galaxies, they often get a Hubble constant value that leans closer to the lower Planck number. This creates a schism even within the local measurement camp, fueling intense debate over which stellar yardstick Cepheids or the red giant tip is more reliable. Is there an unknown systematic error subtly biasing the Cepheid measurements? Or does the TRGB method have its own hidden flaws? Graphs illustrating this tension are startlingly clear. They show two distinct clouds of data points with almost no overlap. One cloud from local measurements like Cepheid-calibrated supernova clusters tightly around the higher value. The other, from the Planck satellite and other early universe probes, clusters just as tightly around the lower value. A vast, empty chasm separates them. The Virgo cluster sits right on the front lines of this battle, its galaxies providing the key data points that both sides use to argue their case. Its proximity allows for the most precise local measurements possible, which only serves to heighten the tension by making the local value even more secure and unshakable. The implications of this unresolved puzzle are staggering. If the discrepancy is real and not due to some hidden error, it means our standard model of cosmology is incomplete. Perhaps dark energy is not a constant but is evolving over time, changing the expansion rate in a way we haven't accounted for. Or maybe there exists a new, previously unknown type of subatomic particle, like a new neutrino, that subtly altered the evolution of the early universe. Some have even suggested more radical ideas, like the possibility that our local region of the universe is somehow atypical, a giant void with a slightly different density that is throwing off our local measurements. The Hubble tension is more than a technical disagreement. It is a potential portal to new physics, a signal that our understanding of the cosmos, for all its successes, is still missing a fundamental piece. And the light from the galaxies of the Virgo cluster is the flashlight illuminating the crack, showing us where to look for the answers that will redefine our place in the universe. From the ghostly grasp of dark matter to the inexplicable pull of the great attractor, from the silent screams of fast radio bursts to the elemental riddles written in hot gas, these 25 phenomena are not isolated curiosities. They are interconnected pieces of a grand cosmic puzzle, each one a different shape that challenges the edges of our understanding. What makes the Virgo Supercluster so extraordinarily valuable is that it presents this entire puzzle box to us right in our own celestial backyard. We don't have to look to the far edge of the observable universe to find profound mysteries. They are unfolding all around us, a local laboratory of the cosmos that offers a front-row seat to the most pressing questions in modern astrophysics. Collectively, these enigmas point toward a future of astronomy that is both exhilarating and humbling. They suggest that new physics is not just a possibility, it is a necessity. Whether it's a fuller understanding of dark matter's nature, a revised theory of gravity, or the discovery of entirely new forces and particles, the clues are there, hidden in the anomalous motions of galaxies, the warping of light, and the whispers from the void. Unraveling these secrets will require more than just bigger telescopes. It will demand a new generation of thinkers, unprecedented international collaboration, and perhaps technologies we have not yet even dreamed of. The path forward is lit by these very mysteries, each one a beacon calling us to look deeper, think bigger, and question more fundamentally. This journey through the Virgo Supercluster's greatest riddles reminds us that the universe is far stranger, more vast, and more wonderfully complex than we often assume. It's a story still being written, and each of us has a role to play in following it. We want to hear which of these phenomena captured your imagination the most. Was it the ghostly galaxy Dragonfly 44, made almost entirely of dark matter, the bizarre multi-tailed wreckage of galaxy NGC 4388? Or the haunting possibility that our entire local universe is drifting toward something we cannot see? Let us know in the comments below. Share your thoughts and your own favorite cosmic mystery. If you enjoyed this deep dive into the unknown, make sure to subscribe and hit the notification bell so you don't miss our next exploration into space's greatest unsolved riddles. The cosmos is full of secrets waiting to be discovered, and we're just getting started.